On this problem, we're asked to find the derivative and well, the second derivative as well, but I really like this problem. What we have is a product rule, this times this, and within that product rule, there's actually going to be a quotient rule inside of that product. This times this, and one of those functions was division. So there lies a quotient rule inside that product. Now, you could have, again, this is a product with a quotient inside. You could have something like, let's see, this is just a completely different problem, but it is possible to have a quotient rule with a product inside, but that's different than what this problem is. This is a product with a quotient on the inside. A quotient with a product on the inside, so a quotient would start off with it having division, and you might have the denominator be x plus 1, and the numerator might be x plus 2 times x plus 3. And see, if we were to take the derivative of this, you would have overarchingly the quotient rule, something divided by something else. But inside of that quotient rule, you would have a product rule on the inside of it. Okay? And that's just something to compare this particular one to. So with this product rule, let's write down what the product rule is. The product rule is f g prime g f prime. So first derivative of the second, second derivative of the first. So remember, your first function is 4 plus 15z over 5z. Your second function is 10 minus z. The derivative of the second function is negative 1, because the derivative of 10, 0, the derivative of that negative z is negative 1. Okay, well, let's go back and do the derivative of the first function. So this is where that quotient rule comes into play. This is where that quotient rule is inside of the product rule. So remember, the quotient rule is denominator, derivative of numerator minus numerator derivative of denominator all over denominator squared. So f prime, again, this is, we're taking the derivative of that first function, is, let's see, the denominator is 5z. The derivative of the numerator is 15. I did the derivative of 4 plus 15z minus the numerator. So 4 plus 15z times the derivative of the denominator. The denominator is 5z, so the derivative of that is 5, all over the denominator squared. So let's see. $75z minus 20 minus 75z all over 5z squared, negative 20 over 5z squared. I will write that as negative 20 over 25z squared, which is negative 4 over 5z squared. It may be even better to think of this as negative 4 over 5 and put the z up top, or out to the side and think of it as z to the negative 2. Okay, so let's work with that. Now that we've finished that quotient rule that was inside of the product rule, let's go to the product rule. So first, and this isn't y, this is w prime. So first function, and notice how the first function is, okay, 4 plus 15z over 5z. You could also think of that, and I think I'm going to rewrite it, as 4 over 5z plus 15z over 5z, which is 4 over 5z to the negative 1 plus 3. And if I would have rewritten that from the very beginning, then I wouldn't have had to do a quotient rule whenever I took the derivative of it. Okay, so first function, 4 over 5z to the negative 1 plus 3. Okay, derivative of the second, so that was negative 1. Plus the second, so 10 minus z times the derivative of the first. So to clean this up a bit and to just distribute some things out, this becomes negative 4 over 5z to the negative 1 minus 3. Okay, I'm going to distribute the negative 4 over 5z to the negative 2 to the 10 and the negative z. To get, let's see, 4 over 5 times 10, that would be 40 over 5. So 40 over 5 is 8. Z to the negative 2 plus 4 over 5 z to the negative 1. When I multiply this 4 over 5z to the negative 2 and a z to the positive 1, this power of 1 and this power of negative 2 add to get together to give me a power of negative 1. And so what happens is the negative 4 over 5z and the positive 4 over 5z to the negative 1 cancel to just leave me with negative 3 minus 8z to the negative 2. And you can leave it like that. You could also put the z squared in the bottom and it would become positive. And now just for our w double prime, the second derivative, we get the derivative of negative 3 is 0, and the derivative of negative 8 z to the negative 2 will give me positive 16, because negative 8 times negative 2 is positive, z to the negative 3. On this next problem, we're asked to find dy dx, and our function that we're going to take the derivative of is 4 sines of x times the tangent of x. So this is going to end up being a product rule. But before we do the product rule on that, let's remember what the derivative of our trig functions are. One hint, a hint that I always like to start off with is the derivative of the functions, the C functions. So cosine, cotangent, cosecant will all be negative. So go ahead and write that down. So the derivative of sine is cosine. The derivative of cosine is opposite sine, and I've already written that negative down. The derivative of tangent x is secant squared x. The derivative of cotangent x is opposite cosecant squared x. The derivative of secant x is secant x, tangent x, and the derivative of cosecant is opposite cosecant x, cotangent x. And a lot of you are wondering about, oh, I've never had trig, or it's been a while since I've had trig. How am I going to take these derivatives? Well, these 6 derivatives that I've just shown you, these 6 rules, you don't have to know trig to be able to use these rules. This is just memorization. If you would like, there are just a few basic trig identities. Now, what I'm about to write down, it's not a derivative. These are trig identities. Some basic trig identities that would be useful to know. Tangent of x is equal to sine x over cosine x. And then cotangent x is just the opposite. It's cosine x over sine x. And it's also useful to know what cosecant x is equal to. It's 1 over the sine of x. And then secant x is 1 over the cosine of x. Those are just some basic trig identities. If I'm not going to make you simplify what your derivative is using these trig identities, but if you would, like to understand that a little bit more, just Google what some trig identities are, and just hit images, and it'll give you a whole list of some of our trig identities that we have. Okay, so this is, again, a product rule. 4 sines of x times the tangent of x. So we're going to be dealing with the first times the derivative of a second times the derivative of the first. Or, excuse me, first derivative of the second plus second derivative of the first. So the first function was 4 sines of x. I just left that constant of 4 with the sine, okay, with the sine x. The second function is tangent. The derivative of tangent is secant squared. The derivative of 4 sines of x, I'm going to leave that constant of 4. And the derivative of the sine of x is cosine of x. So let's say what our derivative is. Y prime is the first, so 4 sines of x times the derivative of the second, so secant squared x, plus the second, so tangent of x, times the derivative of the first, so 4 cosines of x. Right here, do notice there is a GCF of 4, and you're left with the sine of x times secant squared x plus tangent x times cosine of x. And you can leave it just like this. I said you do not have to simplify it using those trig identities, and these were just some of the trig identities that I have written down. I do know that tangent is equal to sine over cosine, so I do think I will rewrite that tangent. And I am putting a box over this because I will accept it like that. But I'm going to rewrite tangent as sine over cosine. And when I do that, this cosine right here, I'm trying to get my arrow, cancels with this one. and I'm left with 4 sines of x secant squared x plus the sine of x. And now, look, now I even have another thing that I can pull out. I can pull out the sine of x, and I'm left with the secant squared x plus 1. This is a question from the test review that says find product or quotient. And I kind of wish I wouldn't have put it on there because it's really tricking some of you up, because what you're trying to do is find a derivative, and that's not what it's asking you to do. It's just asking you to simplify this down. Okay, so find product or quotient. First thing I'm going to do is I'm going to rewrite this division problem as a multiplication problem, and what you can do is change the sign and flip the second fraction. Okay. Now, I'm going to simplify each individual fraction. 50 over 2 simplifies into 25. Okay, now there are 5 w's here basically. W to the 5th means w times w times w times w times w. 1, 2, 3, 4, 5. Okay, and then w to the 6th means, w times itself 6 times. So all 5 of those in the numerator cancel with 5 of them in the denominator and leave you with a power of just w to the 1st. Okay, 10 over 625. Let's see, 5 goes into 10 twice. 5 goes into 625 125 times. And then this w down here cancels with one of those to leave you with w to the 5th. So now I'm going to multiply across, and look, the steps that I'm doing things in, I mean, they don't have to be done in a particular order. I chose to simplify these fractions before I multiplied across, but I could have multiplied across first in this step, okay? But I wanted to simplify first, so you do you, okay? 25 times 2 is 50, w to the 5th, and then w times 125 is 125 w, and that simplifies into 25 goes into 50 twice, 25 goes into 125 5 times, and then this w down here cancels with one of those to leave you with the final answer of w to the 4th. This was an algebra problem, okay? Did not take the derivative at all. But knowing these algebra rules and being able to simplify functions before I take a derivative of them, knowing these algebra rules can help me. They can either help me simplify that function before I take a derivative, or maybe I've already taken the derivative and so now I want to simplify the function. So again, this was an algebra problem, no derivative at all. So this problem says to find the first and second derivative, and I'm dealing with 3x cubed plus 6 over x. Now, do realize I can leave it just like this. I can leave it just like this, and I could use a quotient rule. I could say that, let's see, I could say denominator, derivative of the numerator, minus numerator, derivative of the denominator, all over the denominator squared, and so forth. I could say the denominator is x, and the derivative of the denominator is 1. 3x cubed plus 6 is the numerator. The derivative of that is 9x squared. And I could do a quotient rule. Okay? Or I could say that y is equal to 3x cubed over x plus 6 over x, which is equal to 3x squared plus 6 over x, which, I mean, I could then think of as 3x squared plus 6x to the negative 1, and I could take the derivative of that. And if I rewrite that original function, then I may not have to use a quotient rule. And so if I take the derivative of this, then no, I will not have to use a quotient rule. That's why those algebra rules for simplification that I showed you in the last problem are so important, because they can make finding the derivative easier. So now y prime, I'm not going to use the quotient rule. All I have to do is take the derivative of this, and this is just power rule. 6x minus 6x to the negative 2. And now it also asks for the second derivative. 6 plus, okay, and it's going to be plus because I had to say negative 2 times the negative out front, 12x to the negative 3.